All right, I thought I'd make a video here where I go over the solution to exam 2. So exit out of here and we'll go to the posted solution. Okay, so here was problem 1. I had a block that was sliding down this slope, and we knew a speed here and we knew a speed here, and we wanted to know what the coefficient of friction was, and you're required to use Newton's second law to solve this problem. So because we had 2 speeds and we needed to know the acceleration, because, well, the hint was to know that we needed the acceleration, that we had to use Newton's second law. So we needed acceleration. And we can use the constant acceleration problem here, because if we jumped to the free body diagram and the inertial body diagram, we would see that all of these forces are going to be constant. So that means there's going to be constant acceleration. And that constant acceleration along the line of the slope, which I've called x prime, is going to be just that velocity, the second velocity squared equal to initial velocity squared, plus 2 times that acceleration we're looking for times the distance that's traveled. That could just as easily have been delta x, or we could have called that x2 minus x1 if we wanted to inside that bracket. So we're able to find that acceleration. Then we set up the all-important free body diagram and inertial body diagram. And I really can't emphasize enough to you, for the remainder of your engineering career, if you have any situation where forces are involved, it's a good idea. It's maybe not just a good idea. You should always, always make a free body diagram. And in this case, for dynamics, including an inertial body diagram. But that free body diagram is so important. Anyway, we can set up this equation in the y direction, and we know it's going to be equal to, the acceleration is going to be equal to 0 in the y direction. So I went ahead and wrote this out, but we could also just recognize that some of the forces in the y prime direction, that is, are equal to 0. And then looking at them, focusing in. The reason why we're drawing this diagram, the reason why we're writing these things out, is it forces us to think through and then not miss out on any of the possible forces. It's really the reason why we're beating this drum. And we can see that it's the negative of the weight, which is mass times gravity, times the cosine of theta, because it's along the adjacent edge there of the line. And the only other force acting on the free body diagram in the y prime direction is the normal force, and that's the entirety of the normal force. So we can conclude that the normal force is equal to mass times gravity times cosine of theta. You could, yes, you can just, because it's so simple, you could just jump to this. But many, many other problems you will engage, you cannot just jump to a conclusion. You will need to think your way through it. So I don't want to make a really complicated problem that would make it that would be that difficult now, because it's an exam. But I want to emphasize the very importance of this. Anyway, I beat that drum. And the friction force is, of course, the coefficient of friction times that normal force. So now we go down, and in the x prime direction, of course, that's down along the slope. We will go ahead and put in the values that we find here, and we would found up here that we would got a negative acceleration. You got to be careful with these signs, deciding where, if we're going to follow through with the negative. You could have drawn this if you wanted to, as many people did, in the positive direction, and then wrote the thing out and then inserted a negative acceleration in there. Yes, you can. But the purpose of the diagram is to make us think through the thing. So we just want to make sure we don't go negative and negative, all right? So that would be the big mistake. But I prefer the diagrams as opposed to, the negative we get up here. Okay, that made me write the diagram in that direction. And then, so we have the forces along that axis. We have that friction force. Of course, that's going negative, but the weight is the driving thing that's driving the thing initially probably to move. But it is going to be decelerating. We already knew that from the velocity, so that's how we knew that the acceleration is going there. So we set this up, and we note that the mass is actually canceled out. We could have maybe made the number early on. I think I did when I wrote the thing out. I did it myself. But we note that the mass cancels out. That's sort of an interesting thing, that the thing was going to change. The speed at which it was going to change was not dependent on its mass. Interesting enough. So this is the rubric. I think it's somewhat self-explanatory. I tried to base things on, this is a good way to think about when you're looking at the results of your problem. What did I make on this problem? Well, divide the number you got, obviously, the number of points that you were allotted by 25, and you can see, okay, I made maybe a 70%. Or something on this. That's my way of thinking of this as I'm taking and breaking the things down in concept errors and procedural errors. We go to the second problem here. I'm probably taking longer than you want for this video, but maybe it'll help somebody. I don't know. We have a work energy problem that has lots of the different elements that we're going to be concerned about, and you were required to use work energy. By the way, on this problem up here, yes, you could have used work energy to solve this problem. It's true, but I wanted to measure your performance in doing a Newton's second law problem. That's why I required it. And similarly, you could do this one with Newton's second law, but it'd be quite difficult because you would actually would need to integrate because the force of the spring is not constant. So you would need to have from two different positions, you need to integrate across there for that force. But it is possible to do. It's just kind of annoying. So anyway, and I think Dr. Orlup's class, actually, he had the same problem, but he asked them to do it with Newton's second law. So we're looking at the problem and breaking the thing down. Because I need the forces, I'm trying to be a good role model here. I know what this normal force was. So I went ahead and did a free body diagram and an inertial body diagram because it is dynamic. Although it's not necessary because we're not using the x direction. We're only drawing this diagram to get the normal force, which we know is in the y direction. And so, why would we do a free body diagram? I could just do it by observation. But if you didn't draw this free body diagram, there's a good chance that you missed and you didn't notice that you had to include not just the weight, but also the portion of this force was actually acting to lift up onto the block and reducing that normal force. So here's another instance where even though you're supposed to do this with work energy, you had to find some forces, make a free body diagram. And then we do the constraint relationship, which is a relatively simple one, but still maintained in there with the pulleys. And we know that the velocity of A is going to be 2 times velocity of B. But also if you take that and you multiply it by delta T for a given interval of time, the displacement of A is going to be 2 times the displacement of B. So we apply work energy. It's good to write this out and then to go down this list. So I write it out horizontally and then I come down vertically one after another, ask myself, it starts at rest. We're going to create a datum for this, probably for B, for this mass B right here. We'll call that the datum because it'll have a larger potential energy at state 2. Also, the spring was unstretched in this position, so there's no potential energy there, so that's 0. Then we take a look at the work that's applied. This external force right here, this force is moving this through a distance, but only the horizontal component of it is moving it through a distance. So the distance it travels times that horizontal component is going to be work that's added to the system. So it's positive. But also we have a friction force that's resisting that motion. So we noticed that it's going to be negative right here. It's also energy being removed. We also, we have that delta X in there, but we're told delta Y, so we can replace that delta x with 2 times delta yb. And you notice that I'm just using the absolute value of these because I know the directions that I want to deal with. I don't need to play around with the sign conventions. And the kinetic energy when we're done is going to be both of the pieces, both A and B. And we can substitute the velocity of A is 2 times the velocity of B. So we're able to group these together and find, and we know that that's going to be the thing that we're looking to find. And then the potential energy is going to be both the gravitational and the spring potential energy is going to be greater in the second state. So we put all those together and we're able to solve for that velocity of B2. There should have been a 2 right here. And so we're able to find. And I do believe the problem actually asks for the speed. Yeah, determine the speed. So you didn't need to provide a direction. And there were a number of people that left some things out. That was most of those were like concept errors. You were missing out on pieces. It was a 40-point problem. So generally speaking, I probably would have made this, I hate to say this, a lot of times I would have made that 8 points right there. And then the simple procedural was 4 points. I felt that was maybe a little too harsh. So I chose to go at a lower rate right here. Similarly, actually, on this problem, generally speaking, this would have been 6 points, and that would have been 3 points on a, 35-point problem. A lot of times it'll be like right around 7 points and 3.5 points. It's kind of a little weird. So I kept it at 5 and 2.5 on this. On this last problem, most people did pretty well on this, actually. I thought I was a little concerned. I thought because it was our last topic, maybe people would struggle with it. I tried to make some things a little more straightforward by keeping these the tangential direction. I didn't make angles, so that wouldn't have been that big of a deal. A couple things to note as we're going through the solution of this, right? So, and I like to try to make real problems when I can. So this is what a typical basketball weighs, and this is what a typical baseball weighs. And actually, a typical basketball, I think from the free throw line, I think is 15 miles per hour, and I think it was something like 18 from 3-point, something like that. I looked it up on the internet, so you can look that up too. Just to see, well, how, it's a lot of times with problems, dynamics problems, I think it makes it more interesting to have something where you're taking a real life scenario that could be possible, like a what if thing. If I was throwing a basketball, how fast would I have to throw a baseball to make the thing stop in midair? Right. Well, we could maybe, if we had enough time and motivation, we could probably try this out. So I just went ahead and assumed the positive directions for the velocities after the collision. We weren't asked this in my original problem. I did ask for this velocity. I decided that would have made the problem way too long. So I only asked for the initial velocity of the baseball. So we break this thing down into the x and y, but actually we're breaking it into the normal and tangential. And the tangential remains the same before and after, so we're okay with that. So we take the impulse, initial, impulse, and final right here, and we set these equal to each other. We could see that the we know that the impulse is going to be equal and opposite. Boy, these videos are going to be so great. And I didn't pick my signs right here. I could have. I decided to wait, and I tell you, be careful not to put the negative twice in. I take that VB1 in the normal direction, which is right here, and I replace it. I'm actually using my finger too at the same time. That's really silly. We put the velocity of negative right here because it is going in the negative direction. It's important that we remember that we have a positive and negative here because these are vectors, right? This is a vector problem because it's an impulse and momentum. That's a really critical, important thing to know. So we put them in there, and I'm able to solve for what the velocity of A is going to be after the collision. And I don't know the velocity or speed of A before the collision. I set apply the coefficient of restitution. Here's the equation, and once again I do the same thing as I did up here, and I put those in. And here is where I noticed that it's negative right here. So I can bring out what I'll find right here is I'll get a negative A2n over here, and I was like, okay, that's going to make both of those negative, and because this was negative, I put a negative number in there, so it becomes positive. So here's our two equations, and we can just set them equal to each other with the way that I've written them out. And when we do that, we will find, we're able to find what that velocity VA1 is going to be, right? And or VA in the normal direction. And then we want the actual velocity. Then we could divide by cosine. Here's a critical thing, right? So I wrote that in my critical parts right down here. Important to note. You can't put in, you can up here. You can go ahead and instead of the velocity of A1 in the normal direction, you could just put that it's going to be, yes, velocity A1 times the cosine of theta. But you can't do it right here. Why is that? Because when you apply this E times that, the velocity, times that cosine, right, and times that piece, what you're essentially doing is you're also multiplying it by the tangential one. Right? It's because the tangential one is going to be that VA1 times the sine, right? But now you're only multiplying that E times the cosine when you substitute it in there. So you won't get the same answer if you do this early because you're putting it inside here and you're multiplying this E by it. All right, if that makes sense. Well, in essence, you are dividing it too. So that the E only gets applied in the normal direction. It doesn't affect the tangential direction. So you can't just have this guy by itself in there inside this thing, because it will influence what the answer in the tangential direction is. So you'll get the wrong answer. So that's an important, a minor point, but you have to kind of think your way through it. And you want to be careful in any kind of engineering problem that you're not just coasting and throwing some algebra at stuff, that you're actually thinking about what the actual stuff that's taking place. That's one of the issues that makes the real world much more difficult than just solving and roting and plugging and chugging. So here are the numeric answers for the exam 1. And please look through this carefully, figure out what you did wrong, try to learn from it, and there will be problems on the final exam that deal with these types of things. So we want to make sure that we are able to work through them. Thank you very much, and I hope you guys are being safe, and all your families, and your this is going to be a tough time, so we'll get through it together. Trust me, I'm concerned about your education and about the effect that this is going to have on it. I'll try to do some more fun stuff, and I'll try to keep the I'll send in an email and discuss more about what our plans are. But hopefully you understand why I did the grading the way I did, and that it's not you don't feel put off by the results, and that you think they're fair. And if you don't think they're fair, let's have a discussion with that, please. All right. So take care.